I'm not going to go into who's at fault for missing the class or anything like that, but we need to get far enough today to do some more problems. So, and we also have a quiz at the end today. So I want to spend. So we have a lot. I know we have a lot of stuff that people would probably like to go through. People have questions about the test. I'll go through some of that stuff, but I want to sort of go through it quickly. Maybe I can sort of. So we'll do questions about the test. Maybe I can just sort of give the right path, for test questions if anyone has questions. And then same thing with the homework. If you have questions about the homework, I can just sort of put you on the right path, and then we'll move on to the new stuff. So first of all, the exam. The average was about 80, right in the right ballpark, Anybody have any questions on the test? Problems that have been eating at you since a week ago? Okay. Well, if anything comes up, send me an email or we can talk about it later. And then homework questions. Anybody have any homework questions? I know I talked to somebody about number 2 and 4. I just talked to someone else about 2. So were those? I mean, those were the 2 I didn't have solutions for. Yeah. Anyway, I don't have the problems with me. Anyone have? No. Yeah, it's like 1A. Okay, so problems on differential form of the first law. I just want to point out the beauty and purity of a class that's 4 weeks in and we've discussed one equation. Okay, so first, number 2. So gas is contained in a closed tank. What that means, what you want this to trigger in your mind is, if it's in a closed tank, the volume isn't changing. So the gas isn't doing work through expansion. An electric resistor transfers energy to the tank at a constant rate of 1 kilowatt. Okay, so that's electric work being done. And that's work being added to our system. The gas is the system. And so that means that the sign has to be negative. What? Yes, I already took care of the killa. And heat is leaving the gas at a rate of, so that's given as a function, 5t in watts, where t is the time in minutes. Since it's leaving the gas, that's also negative. This is in watts. And we want to figure out the change in energy as a function of time and sketch the energy versus time graph. So the first law, differential form, says the change in energy with respect to time is equal to the rate of energy being added through heat minus W dot. And so we have dE dt is equal to negative 5t minus negative 1 times 10 to the third. And now you can just integrate that. So the energy as a function of time is going to be the integral from 0 to however long it says. Oh, well, at 0 to t. It doesn't give an amount of time. You just need to come up with this as a function of time. And the integral is, I'm going to use like a dummy variable, but because that's what math teachers always tell you to do here. So you're just integrating that to get energy as a function of time. Any questions about that one? And then 4, well, let me just go through my thing and then you can ask what came up. So we have 1 kilogram of refrigerant that has initial. Yeah. Yeah. Okay.
Does it matter at all that the differential form of the first law is defined in seconds, given in minutes?
Yes. Yes, it does. It does very much. So yeah, you have to do that conversion. T is time in minutes, so this is going to be, I guess you could think of this as 60t. Yeah. So for number 4, you have a refrigerant. The total amount is 1 kilogram. And it has an initial pressure of 0.9 megapascals and a specific internal energy at that first instant of 232.92. That's in kilojoules per kilogram, so I'll write that like this and do it in joules per kilogram. And again, we have a closed tank. And so that says no volume change. And no work from expansion. A paddle wheel inside the tank. So you could think of the total work as being the work done by this paddle wheel plus the work of expansion, and that's the one that goes to 0. The work done by the paddle wheel transfers energy at a constant rate of kT in kilowatts, where time t is in minutes. And it's transferring it to the refrigerant. Our system is the refrigerant, and so this has to be negative. So we have negative So we have K times 10 to the third times T, and then we're in watts, and T is in minutes. So I'm going to write this as 60 K times 10 to the third times T, where T is in seconds. Just getting all the units the same. Is that? It gives the time in minutes, so let's leave it in minutes for now. Okay, so this is in minutes. Any questions so far? After 20 minutes, the refrigerant. So after 20 minutes, we have a new pressure. P2 is 1.2 times 10 to the 6 pascals. We have a new internal energy, specific internal energy, of 276.67 times 10 to the third joules per kilogram. There's no change in kinetic or potential energy. And we want to find what K is, and we want to find Q and W. Okay, so the first law in differential form says dE dt is equal to Q dot minus W dot. And it says there's no change in kinetic or potential energy, so this is all internal energy. So du dt is equal to Q dot minus W dot. And if we integrate this equation, time equals 0 to 20, then what we get is that the change in internal energy is equal to the integral from 0 to 20 of Q dot dt minus the integral from 0 to 20 of W dot dt. And the reason that we want to integrate this here is because we know what this is. We're given internal energies, specific internal energies at those two instants. Okay, so that says 276.67 minus the initial internal energy, 232.92, 232.92. And that's all multiplied by the mass, which, well, is 1. And then times 10 to the third. So that's the change in internal energy. I'll put the 1 here so you remember that that's a specific internal energy. That's equal to, well, what do we know about it's a closed tank. No change in kinetic or potential. And that's equal to the integral from 0 to 20 of q dot dt minus the integral, we can write that as just plus k times 10 to the third times t dt from 0 to 20. Okay, so we have an equation here that this one you can think of as the heat added to the gas in those 20 minutes. This one you can integrate, and you get 0.5 times 10 to the third, piece, and then times 400, I guess. And then K. Okay, so we have one equation and two variables, and that, I assume that was what you ran into. Okay, one equation and two variables, but we haven't used anything about the pressure yet. Mm-hmm. Well, we're this T has units of minutes, so I just kept everything minutes, so that should be right, I think. It's contained in a closed tank. I don't see a way out of that.
Just assume, kind of assume a volume for the tank, and then
we don't even know, like, we don't know anything about that refrigerant. We don't know whether it's, we don't know whether it's a gas or a liquid. So
say we know that it's
okay. So the last thing we were talking about was properties of simple compressible substances. And if you have a simple compressible substance, the entire state can be specified by just giving two properties. Which means that you could do experiments and choose any two properties you want, and there are lots of properties. Internal energy is a property, volume, pressure, temperature, entropy, enthalpy, things that we're going to talk about later. There's all these properties, and if you know two of those, you can specify all of them. You'd have to do experiments to find those relationships, but two is all you need. And because of that, that allows us to draw a PVT surface. PVT surface, and you know the thing with any surface is you only have two independent variables in a surface. And then we went from there to projections. And the projections, we had the phase diagram. Who remembers what variables were shown in the phase diagram? Pressure, yep, that's right. Pressure and temperature. And then second, we had the pressure volume diagram. And then TV guide or TV diagram. And we'll use these three projections in different ways, but all of them give you, let you visualize regions where a simple compressible substance is in a certain phase. And so now I need to talk about phase change. So for us, phase change means going back and forth between solid and liquid and gas. For us, this is going to be more important. And so I'm going to just talk about the liquid phase and the intermediate state where your system is part liquid vapor, part vapor and part liquid, like steam with water dripping, down the sides of the vessel or whatever. That would be halfway in between. Oh, by the way, if you're going this way, this is freezing. If you're going this way, it's melting. If you're going this way, it's condensing. And if you're going this way, it's boiling. It does. Well, it's not going to for us, but yeah, I guess that's true. My diagram would look sort of messy with that, but solid to gas is sublimation. But you can see that on the PVT surface. You can see where sublimation happens. Okay, so let's first talk about liquid, the liquid phase. And let's talk about increasing the internal energy in a gas with constant pressure. So hold the pressure constant. Increase the internal energy in the gas or in the liquid. You get a big increase in temperature as you put energy in. And you do get an increase in the specific volume, but it's really small. The space that a liquid takes up basically stays the same. So the volume barely increases. Until you get to the phase change temperature. So then you reach the boiling for that pressure. And you get to the two-phase state. Well, I guess before it changes to two phases, the boiling temperature. What's the name of a liquid that's at the boiling temperature, but it's still, that's right. So you get to a saturated liquid. And now any energy you put into the saturated liquid starts turning that liquid into gas or vapor. So if you put more energy into that saturated liquid, the temperature stays the same. And the volume changes a lot, increases a lot. Throughout this whole two-phase state, throughout this whole region of the process, any liquid that's in there is saturated. And vapor is saturated. Anybody, this isn't really like a technical thing. It doesn't really matter for how you think of it, but does anyone know the difference between what people call a vapor and a gas? You heard of that before? They have the same meaning, but people tend to talk about a vapor when they're talking about a substance that at room temperature or whatever, at the working temperature, the base temperature, the material is either a solid or a liquid. So right, so oxygen, you'd say, with that way of thinking, oxygen is a gas and steam is a vapor. Yeah. So this is really important. So why is it that we're only dealing with liquids and gases or vapors in thermodynamics? The key thing is that how do you get that energy for the, I mean, you can do it with work, but often the way that you're changing the energy in a substance in order to make this phase change happen is through heat. And heat is energy that's transferred through a temperature difference, okay? But so, like if you have a liquid that's at 15 degrees and you have a heat source next to it that's at 20 degrees, okay, and you're trying to raise the energy in that liquid by holding them next to each other with a copper thing between them or whatever to exchange energy, that liquid's temperature is going to rise, and as it rises, there's going to be a decrease in how quickly energy transfers. Once the water gets to 19.9 degrees, there's barely going to be any energy transferring back and forth due to this temperature difference. Okay, but now imagine that you have a liquid that's right at the boiling point. Okay, and it's at 15 degrees. You know, that would have to be some substance and at some pressure where that's right at the saturation temperature. But you have this liquid, and next to it you have this heat source that's at 20 degrees. And now there's a 5-degree temperature difference, and it's just pouring that energy into the liquid, turning it from liquid to gas, without decreasing the efficiency of that energy transfer. Do you know what I mean? Because it's poured in a whole bunch of energy to turn a lot of that liquid into gas, and it still has the same temperature difference that it did at the start, you know? And so that's really like at the heart of why thermodynamic systems, like what is it about, like why do air conditioners, refrigerators use refrigerant 123A, or why do they used to use Freon and whatever? Why not just use water? Well, it's because at the operating temperature and condition, those are substances that it can keep right at that phase change temperature. So how am I going to say that? This is important. This is important to us. Because heat requires a temperature difference. And putting energy into a saturated liquid doesn't change the temperature difference. The same thing happens in the phase change between solids and liquids. So if you have a saturated solid and you increase its internal energy, the temperature doesn't change, and it little by little turns into a liquid. The amount of energy that's required for that phase change is a lot less, though. So there's a lot of energy that you can store in a. So when you go from a saturated liquid to a saturated vapor, you're storing a ton of energy in that material without changing its temperature. When you go from, that's called the latent heat. When you go from a saturated solid to a saturated liquid, you are storing energy, but not nearly as much. And the reason you're not storing as much is because where that energy comes from, you can think of it as potential energy between the bonds of the molecules. A solid and a liquid, those bonds are changed, but the things stay pretty much the same distance apart. There's not a big change in volume as you go from a solid to a liquid. Yeah, that's what I'm talking about. That's right. That potential energy. That's right. Yep. Think of it as like gravitational potential energy, you know. And so you're not changing. So to move things from here to here, you don't have to put that much energy into it. So you can't store that much that way. If you go from saturated liquid water to saturated water vapor, you have to increase the specific volume something like a factor of 3,000. It's not this to this anymore. It's this to, like Chipotle, you know. So, because of that, this we're going to be dealing with the uh, the phase change between liquid and vapor, and we're going to introduce this term called quality for substances that are in this phase change region. Quality X is just equal to the mass of vapor you have in your system divided by the total mass, or I guess I'll write it as the mass of the liquid plus the mass of the vapor. And if what you're trying to do, like you often are in heat engines and things, is you're trying to use the internal energy in your system to do work, this is a real sensible idea for like something that a system that you consider to have high quality to be useful to you is one where a large fraction of your system is a gas, because that means that much of your system has energy stored and ready to do work. Okay, so question. What's the quality of a saturated liquid? Zero, yep. And what's the quality of a saturated gas? Saturated vapor? 1, yep, exactly. And any mixture of those two things is somewhere in between those two extremes. So the internal energy of the system increases until the quality is 1, and all of your system is a saturated vapor. And if you increase the internal energy more, you get to a superheated vapor. Adding energy at this point leads to big volume increases and big temperature increases. And I should say, the way I'm thinking about this, when I talk about big or small volume and temperature increases, I'm imagining doing this in a constant pressure environment, which is the way, like if you're doing experiments in your kitchen or whatever, that's what you do because you have atmospheric pressure. So it's sort of a natural way for us to think about it. But obviously, you could do these phase changes by changing volume in the temperature. So superheated vapor, um, that's just vapor where you've gone beyond the saturation temperature and you're just heating it up farther. We, like with steam, we think of I don't know. I think we're sort of used to thinking of steam as this visible gaseous thing, like you can see it coming out of a teapot or whatever. But the reason you can see it is because that's saturated vapor, and as it hits the air, it's just immediately condensing. And what we see is the condensing of, but a superheated water vapor is invisible. It just joins the gas in the room, which is why people say, you should be careful if you try to mess with superheated steam because you can't see it. You can't see where it's safe to put your hand. I think if you keep cranking your teapot, you will see a little region coming out of the spout of your teapot where you don't see anything, and then you're like, well, why is the steam coming out of nothing? There's like nothing, and then there's a cloud of steam. That's a little region of superheated stuff before it starts to condense. Okay, so let me. So, what do I want to look at? I want to look at the TV diagram. And this is a nice way to look at phase change. So this is what we're talking about. These lines here are constant pressure lines. So like one of these is what you're doing if you're sitting in your kitchen with an ice cube and going through all the phase changes. Volume, specific volume is down here. Temperature is here. And what you're doing to follow one of these dotted lines is increasing the internal energy. So you can see that in this compressed liquid region, so I guess this is only liquid to gas, so I said an ice cube, but this is starting with a glass of water. But if you increase the internal energy in the gas, you get big changes in temperature and very small changes in specific volume. That's because liquid water's volume doesn't change very much as you increase its temperature. Then you get to the saturated liquid. You get to the boiling point. And at that point, you enter this region that's so useful in thermodynamics, where you can add all this energy and store this energy without changing the relationship between the temperature of your system and its surroundings. And then you get to finally, you get everything to be a saturated vapor, and increasing the internal energy from there increases the temperature and the volume. The volume's increasing at a faster rate than it was here. You can see that's steeper and that's shallower. So this temperature volume diagram is a nice way to look at the phase change, understand what's happening there. Anybody have any questions about that? Okay, so yeah, yes.
I was a little late on the ball.
Mm-hmm.
I'm just having a hard time. Go back to the diagram.
Yeah.
Okay. What exactly do those dotted lines are constant?
Yes, okay. That's right. So that's this is one of you doing this experiment in your kitchen, and this is one of you who lives on Mount Everest doing the experiment in your kitchen. Actually, that was a joke, but on Mount Everest, mountain climbing people, it's an issue they have to deal with. That if you're at a lower pressure, like this, the temperature at which stuff starts to boil is lower. And if you're at a way lower pressure, like you are on Mount Everest, the temperature is so low that, you know, they're trying to cook their noodles or whatever, and it's hard enough to motivate to do stuff, and they're trying to cook their food, and water's boiling at 70 degrees, which won't cook anything, you know? Yeah. Oh, yeah, well, I think, yeah. Yeah. Well, that's because that's because your body still hasn't changed to that pressure, you know? That's why, like, on an airplane, did I already say this? On an airplane, have you ever noticed when you get a bag of potato chips on an airplane, it's puffed up, it looks like it's inflated? That's because they do pressurize the cabin, but not all the way. And so they pack these, and they look normal at sea level, and then at the lower pressure, there's a higher pressure inside the bag, a lower pressure outside, and it inflates like a balloon. All right. So now we're going to take advantage of the fact that with simple compressible substances, remember, 2 properties is all you need to specify all of the properties. So I'll say it like this: 2 properties uniquely define a state. And the way we're going to take advantage of that is property tables. So for a bunch of different substances, people have mapped out for, you fix 2 of those properties, pressure and volume, or pressure and temperature, and internal energy, and enthalpy and entropy, and all these other properties are specified or can be specified, just based on experiments. So property tables are going to relate temperature, pressure, specific volume, and specific internal energy, and also specific enthalpy and specific entropy. Those will be important later. And for any material, we're going to use 3 different tables. The material we're going to use most of the time is water. So for a given substance, we'll use 3 different tables. The first one is called saturation tables. These can be listed, I guess I'll say indexed by temperature or pressure. So we'll have pressure tables and temperature tables. And based on that, it lists the properties for saturated liquids and saturated vapors. So for this one, for the saturation tables, they're the easier ones to use because you don't need to specify two properties. And the reason you only have to specify one is because we're requiring that we're at that saturation state. So at a given pressure, there's only one temperature that will have you at the saturation point. So these are easier to use because they're indexed by a single variable. And then the other two tables, like you can imagine, are for compressed liquids, which is a liquid, and then superheated vapor. So a compressed liquid.
So when you say compressed liquid, it's no different than saying
Liquid, yeah, it's the same thing.
it doesn't imply that it's not saturated or anything.
No, compressed liquid is liquid.
Okay.
Yeah. Yeah, in the yeah. So what's
purely curious?
Yeah, right. I don't know where that comes from, but yeah, we should just say liquid, except the tables say compressed liquid. These are listed by like in sections. So each section is for a given pressure, and then in that section it's indexed by temperature. So now we're sort of trying to use these tables to search a two-dimensional space, and that's why it's sort of tedious. And then the same thing happens with the superheated vapors. Well, I know why it says compressed liquid, because it's making a distinction between a compressed liquid and a saturated liquid.
Oh, okay.
Yeah. So you can have a liquid and still be at the saturation temperature, and if you're not, then you're a compressed liquid. And this is done the same way. So there are sections that are defined by pressure, and then inside that section, you're indexed by temperature. So I will put these tables on D2L. But here's an example of, so there's a saturated, okay, so here's the saturated table from the book. Probably not it's just this one. I figured out how to use the scanner better, so I'll do a better scan. But this one is, so this says it's the temperature table for saturated water, which means that everything's indexed by temperature, and it gives all the other stuff according to that temperature. And notice that there are columns here for, I can't read that either. There's a column for, saturated, so for each thing, there's specific volume for a saturated liquid and then for a saturated vapor, and you have to use whichever one of those two columns is relevant for you. For each one of these things, specific volume, specific energy, enthalpy, entropy. And so that's easy to use. Here's the question, though, and this is what we're going to spend a little time on after this. Even though this one's easy to find what you're looking for. 23, 20. What if you want to calculate these things at 20.5 degrees? It's a table. It's not continuous. So what do you do? And we're going to have to use an interpolation method for that. Now let me show you the other kind of table. The compressed liquid tables and the water vapor tables, the vapor tables look sort of the same. But here's what I mean by sections. So there's a section here at a specific pressure of 0.006 megapascals, and then inside that section it's indexed by temperature. But what if you want to do it at a pressure of 0.25 bar, and you want to do it at a temperature of 170 degrees? Again, it's not a continuous table, so we're going to have to use an interpolation method. Well, how would you do it if you worked at a company that where you had to calculate these properties based on temperature and pressure and whatever? Clearly, you would have software where you just plug in what you want and it just spits out the answer, And that software, I'm sure, is available online. I am going to spend a little time going over this interpolation method, though, not because it's important for using these tables, although that's what we'll use it for in this class, but more because it's a numerical idea that's going to come up a lot in your future classes, numerical methods classes and things. And I think it's a nice way to think about linearizing problems. Okay, so linear interpolation. Computers are not good at continuous things. They're good at repetitive, finite things, and so almost any engineering computer-based solution is based on some kind of linear interpolation. Finite element analysis to calculate stresses and strains is based on breaking up a body into just tons of little chunks and then just calculating values at those little chunks. It can do that really fast, And so the idea of linear interpolation is this. We got to get to this quiz here soon. Let me just draw this picture and then we'll move on. So let's say that you have this function and you know the value here and you know the value here and you want to get the value here. Then the approach you take is you assume that between the two things you know, the function is piecewise linear. Based on the fact that you're assuming it's linear, you approximate the value here. Okay. So I think you should be able to figure out the rest. That's the idea. Not really. I'll tell you how to do it, but that's all I can.